Hello everybody. So what we're going to be looking at today is going to be sequences and limits. Now, this is a very interesting topic, and one thing you'll notice about it is that it's not integration. Okay, so we're done with integration in this class. So we are done with integrals. All right, we're on to a new chapter. So done with integrals in Math 4B. New thing. What's the new thing? Sequences and series. And we're doing sequences and series not because we care so much about sequences and series, but what we want to get to is something called Taylor series. Later on, Taylor series. Okay, so so new thing, done with integrals. So you've done all of your integration, you'll have a test on it, and new thing. So let's talk about it. So in this section, we're not talking about series yet, we're only talking about sequences. All right, now what is a sequence? What is a sequence? Well, it's actually very easy. A sequence is simply an ordered list of numbers. Usually, but not always, usually it continues on forever. So what's that mean? So like a sequence might be this: A1, A2, A3, A4, A5, dot, 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 dot. That could be a sequence. Now, all of the A's, A1, A2, A3, A4, A5, all of those are just numbers. Okay? Now, you'll notice that I used curly braces. Not every book uses that notation, but it's pretty standard. So it's kind of this, when you have set notation, you use curly braces. And technically a sequence has an order. Like if A1 comes before A2, you have to write it before A2. But, so technically it's not just a set, but it's a lot like a set because it's just a list and a set is a list. So they're kind of the same. But regardless, they often use curly braces around a sequence. Sometimes they'll write it this way. They'll say AN like that to refer to the sentence or sequence. Sometimes they write something like this. Try to move you down here. To refer to the sequence AN. All right. So anyway, basic notation there. Now, what you're going to see is that they're any kind of list of numbers. So like a couple of sequences that we could write. Let me I need to see this real quick. Mute. Okay, sorry. So I just wanted to make sure that they used curly braces, and they do. So they use curly braces, we're using curly braces. So they write AN to refer to the sequence AN. Here's a couple of examples of sequences. You could say like AN is 1, 2, 3, 4, dot, dot, dot. The dot, dot, dot is just to indicate that it keeps going. This means it keeps going, and you're supposed to know how it keeps going. So you're like, if it says 1, 2, 3, 4, ... you're supposed to pick up on the pattern. Okay, so there's a sequence. Now, what you're going to have to do is you are going to have to come up with the formulas of a sequence in this section. So if they give you a sequence, you might, not might, you'll have to, you might have to come up with the formula for the general term. Now, when I say the general term, what I mean is a formula for an. Okay, so what does one of these look like? Let us see. Well, actually, before we come up with a formula, let's just look at an example of writing a couple of terms, right? So let's say I say this. Suppose we have a sequence an where an equals 1 over n squared. Okay? Write the first 5 terms of the sequence. Right? And the idea here is that you have a formula. So this is a formula that you use to calculate the terms, right? Use the formula. So that's what we're going to do. We're going to use the formula to calculate terms. So it's easy enough to do. Like, what is A1? Well, you've got, let me erase this. You've got the n right here, and then you've got an n right here, right? So if I put a 1 where the n is, then I should put a 1 where the n is in the formula. So it's 1 over n squared, but that's going to be 1 over 1 squared, right? So there's your n. And if you want a2, that would be 1 over 2 squared. And a3 would be 1 over 3 squared, right? 3, 2, 2, because that's what the formula says to do. And you can keep doing that. We have a 4, 1 over 4 squared, and a 5, 1 over 5 squared. And of course, you can actually calculate those numbers. That's easy. This one's 1. This one is 1 over 4. This one is 1 over 9. This is 1 over 16. And this is 1 over 25. So it's easy to calculate the terms of a sequence if they give you a formula, right? So that should not be a problem. Going back the other way is a little bit trickier, right? Guessing the formula from the numbers, right? I don't want that color. It's a little tricky to come up with the formula yourself. When given numbers. So what you want to do is be able to recognize certain common things. So like, here are some common things you might do. Common formulas, I guess. So you see this, like let's say 1, 2, 3, 4, ... you can probably guess that that's going to be like the formula there is just an equals n, right? Sorry, trying to figure out what the way I want to write this is. Okay, does that make sense? 1, 2, 3, 4 is just an equals n. You know, if you did this, how would you do, 2, 4, 6, 8, how would you do that? Well, the way to do that would be to make it count up by 2's, you'd have to do 2n, right? Because this is the n equals 1 term, and this is the n equals 2 term, n equals 3 term, n equals 4 term, right? So to make it count up by 2's, you have to multiply the n by 2. Now, if you have, it's obvious how to continue that, right? Like if I do like 5, 10, 15, 20, ... you can just say, oh, well, that is 5n, right? But what if you kind of change that around a little bit? What if I go 3, 8, 13, 18, 23, 28, ... So this is a little bit weirder, right? I'm counting up by 5's, right? Plus 5, plus 5, plus 5, but it's not just an equals 5n, right? Because 5n would start at 1. Sorry, 5n would start at 5. So what you have to do is say, like, okay, well, it's 5n. It's 5n because it counts up by 5. But when you put in a 1, you're going to get 0, right? We don't want 5, or sorry, did I say when you put in a 1, you get 0? When you put in a 1, you get 5. You don't want 5. When you put in a 1, you need to get 3. So if you put in a 1, you get 5. You need 3. So just subtract 2. So this counts by 5's. So 5n counts up by 5's, and then the minus 2 makes sure we start at 3. Makes it start at 3. Okay? So that is that's how you could do that. Of course, there's lots of other patterns that you need to see. So that is just if it counts up by the same number every time. What about something like this? 1, 4, 9, 16, 25, ... What's that? Probably you already know, maybe. That is an equals n squared, right? You can recognize the perfect squares. And of course, you can recognize perfect cubes as well. Like 1, 8, 27. What's 4 cubed? 64. What's 5 cubed? 125, ... You might recognize that if you see those numbers. But not everything is n squared, n cubed. Sometimes you have exponents too. So if you see something like this, 1, let's see, 2, 4, 8, 16, 32, ... It's sometimes hard to tell the difference between something like this and something like one of the ones that came right before it. But here you would need to recognize that 1, 2, 4, 8, 16, 32, those are all powers of 2. So that's like 2 to the n, right? The difference is where's the n? In the exponent or in the base? But you need to recognize that kind of thing when you see it happen. Otherwise, you're not going to be able to, get the right formula. What else can we get? Well, what if you have something do this? What if I go like 1, sorry, yeah, that's fine. -1, actually. 3, No, I changed my mind again. I'm sorry. -3, +9, -27, +81, -243, I think. What's going on there? Right? There's two things going on there. First of all, you should realize that these are powers of 3, right? That's 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, right? So you can guess that that is 3 to the n. But what about the minus, plus, minus, plus, minus? What about that? Okay, and so the way to make that happen is to realize that you actually want it to be -3. Because if you have -3, right, A1 would be -3 to the 1, which is -3. A2 is -3 to the 2. -3 times -3 is +9, right? And so what happens is, if you put the negative inside those parentheses, that's going to make it alternate sign, minus, plus, minus, plus, minus, plus. Okay? And in fact, you can make any sequence alternate sign with something similar. So you can make any sequence alternate sign, plus and minus, with either a -1 to the n or -1 to the n plus 1. So as an example, let me just write another series here. What if I have, let's see, 1, 4, -4, +9, -16, 25, -36, ... Right? We already know how to do the basic pattern there in terms of the 1, 4, 9, 16, 25, 36, right? We've seen that already up here. It's just n squared. So you go, okay, well that is just n squared. But n squared is not going to go plus minus plus minus plus minus. So the way you make it go plus minus plus minus plus minus is with one of these guys. So I start out just by writing -1 to the n. But then what I want to think about is, when I write -1 to the n, is that actually going to give me the signs that I see there, right? Because if I check A1, I see -1 to the 1 times 1 squared, which is actually -1 when you look at it, right? And I'm supposed to have a +1, not a -1. So actually when I went -1 to the n, that was wrong. What I need there to fix it is, instead of a 1, I should have had a 2. Then it would have been +1, right? Well, how would I make sure that I get a 2 there? Well, when you plug in a 1, you want it to be 1 plus 1, and then it'll be 2. Okay, so you use this one or this one depending on whether you need the first term to be positive or negative. And just write it this way, and then just see if you need to change it afterwards. Okay, so that's how you can make it alternate sign. Okay, let's do a couple of these. Let me see if I can find ones that look like the homework. Oh, just let me go. You're killing me. I need to go back to the beginning. That's what I need. Too far. Next. Preview. Cheat. Cheat? Oh no, there we go. There we go. So the actual problems are kind of, they have more than one thing going on in them. So like, here's an example. 5 over 6, negative 25 over 11, 125 over 16, 625 over 21, that's negative, positive 3125 over 26. Now we want to, and they say note A1 is 5 over 6. That's just so you know that the first term is A1 instead of like A0 or A3 or something like that. So they just want to make sure you know that we're starting counting at n equals 1. All right, and what are we supposed to be doing? We are supposed to be finding the formula. For an. All right, so let's see here. What you want to do is just think about the numbers on top and on bottom separately. So first thing is forget the pluses and minuses. I don't care about it right now. Let's just look at the top. Let's go, nope. Let's go 5, 25, 125, 625, 325. What are those numbers? Let's think about it. So of course the 5 is 5 to the 1, right? And the 25 is 5 to the 3. No, it isn't. 5 to the 2. The 125 is 5 to the 3. You can check this. 625 is 5 to the 4. Is that true, right? Check it. It is. So I think I've got the pattern there, right? So I think I know the top. So we have AN is, well, 5 to the n. There we go. Got the top. Okay, now what's going on the bottom? Now on the bottom, what are we doing? They don't look like powers on the bottom, do they? Right? So like the 6, 11, 16, 21, 26, those aren't powers. Those aren't powers of anything. What are they? Well, you should notice that we're just adding 5, adding 5, adding 5, adding 5. So how do you add 5? Well, we already saw that, right? We saw that up here, right? Like 5n will add 5 every time. So that's going to be 5n. But if you do 5n, you're not going to get 6 as your first number, are you? If you do 5n, your first number is going to be 5. So how do you fix that? Just add 1. Now, the 5n makes it count by 1. Sorry, the 5n makes it count by 5s, and the plus 1 makes it start at 6. Because you'll plug in a 1, you'll get 5 plus 1. You can check that when you put in like a 2, what are you going to get? 5 times 2 plus 1? That's 11, which it should be, right? 11's right there. So you can check it and see that that will actually give you the 6, 11, 16, etc. So that's good. So we have the top number, we have the bottom number. The only thing we haven't dealt with is to make it alternate signs. So we need a plus, and then a minus, and then a plus, and then a minus, and then a plus, right? I highlighted nothing on 3 of those, but we need a negative sometimes. So we'll do that, -1 to the n. But remember, -1 to the 1 is -1. So you look at the first term and see that its first term is positive. First term is positive. So when I plug in a 1, I need to get a positive number. I'm going to get a negative number unless I change this to n plus 1. So I did everything now. It alternates sign. The top's powers of 5s. The bottom counts up by 5. And that's everything it needs to do. So that's my answer. Okay. So that's how you do those. You need to recognize certain patterns. Let's try another one. Maybe it'll go faster. Let's see. So same thing. -1/8, 2/15, 3/22. That's -3/22. 4/29. -5/36. What is the pattern? Well, let's just look at the top. Top is 1, 2, 3, 4, 5. Okay, I bet I can do that one. 1, 2, 3, 4, 5. That's in. All right. Now, in the denominator, though, the denominator is more complicated. It goes 8, 15, 27, 29, 36. Again, that doesn't look like exponents to me. So if it doesn't look like exponents, I'm going to hope that it just counts up or something. So from 8 to 15, what do? You add 7, right? And from 15 to 22, you add 7. Add 7. Add 7. So the way to do that is 7 in. Now, just like the other one, we need to make sure that we actually start at 8. So it starts at 8. So if you put in a 1 right here, you're going to get 7. How are you going to make it so you get 8 the first time? Add 1. Okay? So that's going to give us the numbers on top and the numbers on bottom. It also alternates sign. So how are we going to do that? I mean, I bet you can guess because we did it already. -1 to the n. Now, should it be in or in plus 1? Think about it. Well, if you do -1 to the 1, you're going to get -1. So right now, the first term, it should be negative. But the first term is negative, and we want it to be negative, so actually that's good. So this must be done. Right? Alternate sign, top counts by 1, bottom counts by 7, and then we just add, subtract the 1 to make it work out the way we want. All right. So those are pretty straightforward. I think take a little bit of practice, but there's not too much variation. So you'll get better at it with a little bit of practice. Now, another thing you're going to see is what we call recursively defined sequences. Now, what a recursively defined sequence is a sequence where the formula for an refers to earlier entries, or earlier terms of the sequence is how I'll say it. So the way you'll see it is something like this. Example, they'll say A1 equals 6. So they're not telling you AN, they're telling you A1 equals 6, and then they tell you AN is AN minus 1 minus 3 for n greater than or equal to 2. Okay, so if I want to write out, like, let's just say 4 terms. Okay, just because I want you to. So the way this works is as follows. So they gave you one term to start with, right? So you know what A1 is because you were told A1 is 6. Okay, now, of course, then we want to calculate A2. Well, how do you calculate A2? Well, this right here, if you put in a 2 for the n, right? We have a 2 there. So if you put a 2 there, then you also have to put a 2 there, right? Because that's what the formula says, n is n. So if you put a 2 in for n in one place, you have to put a 2 in for n everywhere. So A2 is going to be A 2 minus 1 minus 3. But that is simply A1 minus 3. But A1 minus 3, we know A1 is 6, right? They gave it to us. So 6 minus 3. So A2 is 3. Do you see how this works? We might actually do more than 4. But so the formula, when they say this, an equals an minus 1 minus 3, the more you write, the more confusing it is. Like, all we're saying is this. If you want to calculate A3, it's A2 minus 3, right? And if you want to calculate A4, it's A3 minus 3. And if you want to calculate A5, it's A4 minus 3. That's what the formula is saying up here. An equals an minus 1 minus 3. An minus 1 was the last one that you calculated. So if you actually calculate these, then you have A3 is A2 minus 3, but A2 is actually right here. So 3 minus 3, which is 0. And then A4 is A3 minus 3, but what's A3? It's what we just calculated. A3 is 0 minus 3. So minus 3. And then A5 is A4 minus 3, but what's A4? A4 is minus 3. So A3 minus 3, which is negative 6. Okay? So that's a recursively defined sequence. So you wouldn't be able to calculate like any term that you wanted, right? So if somebody wants you to calculate, if you had to, like a 100 or something, it would be really difficult. So it would be hard because, you know, A100 by definition is A99 minus 3. But you don't know A99. Right? A99 is A98 minus 3. And so on, right? So the point is if you wanted to calculate A100, so if you wanted to calculate A100, you actually have to start at 1 and count every single one from 1 to 100. You need to start with A1 equals 6, that's what it was, and compute all of them from A1 up to A100. So that's weird. Well, not weird, but I mean that's how it works. So it's recursive. Recursive means it refers to itself. So the formula refers to itself. Okay? Now, they might have you calculate a few of these. They might have you calculate a few of these, but what they're really going to have you do, which is hard, is like this is not a good property, right? Like this property that if you wanted to calculate A100, you have to start from A1 and compute all of them up to 100, right? That means you, like, if somebody says, oh, what's A500? Well, hold on, I just need to calculate 500 of these in order to tell you what A500 is. That's not good. So what they want is there a formula that's not recursive? So it's important to be able to find those. So it is good to be able to find a non-recursive formula, which the book will refer to as an explicit formula. And you could call a recursive formula implicit, but nobody does. So it's good to be able to find a non-recursive formula, an explicit formula, for a recursive sequence. So as an example of that, let's just take the one that we just looked at. They say A1 equals 6, AN equals AN minus 1 minus 3. That's for n greater than equal to 2. And, find an explicit formula. For AN. Now, if you have to do this, what your steps are is the first thing, step 1, write out some terms. All right, so you should go A1 equals 6. A2 is A1 minus 3, which is 6 minus 3. Which is 3. A3 is A2 minus 3, which is 3 minus 3, which is 0. A4 is A3 minus 3, which is 0 minus 3, which is minus 3. A5 is A4 minus 3, which is negative 3 minus 3, which is negative 6, right? And so you do this until you think you see the pattern. So step 2 is we're going to look at these and see if we can tell what the pattern is. So let's just write them out. So they were 6, 3, 0, minus 3, minus 6. Okay, so let's see if we can do it. So the pattern to me looks like we're counting up, well actually down, but we're counting down by 3, right? This is like minus 3, minus 3, minus 3, minus 3. And we have a pretty good idea of how to do that. So AN is, well, what counts by 3s? 3n counts by 3s, right? But we're counting down, so it actually should be negative 3n. And if you put a 1 in there right now, right? Like if you do A1, negative 3 times 1 would be negative 3, right? But it actually starts out at 6. So what would I have to add to it to make it start at 6? How about 9? Right? So what you're thinking of is this counts down by 3s. And we add 9 so that it starts at 6. And that's your pattern. So that's your formula. Okay. So it's kind of like the problems that you already did. It's just that you have to write these down. Okay. Now they actually have a better way of doing this. That's going to be more useful, I think. So maybe I'll do that real quick. A better way, maybe. So we still calculate it the same way. A1 is 6. A2 is 6 minus 3, right? But what they do is instead of calculating this, so like don't simplify this. Okay, so A3, you know, is A2 minus 3, right? So what you want to do is put that in for the A2. So it's 6 minus 3 minus 3. And that can be written as 6 minus 2 times 3. Right? Minus 3 is minus 2 times 3. Now, I'm sure you probably don't see what I'm doing yet, but it will become obvious soon. So I leave it like this. And then for A4 is a 3 minus 3. But you're going to take this and you're going to put it in here. So you're going to have 6 minus 2 times 3 minus 3. But that, with a little bit of effort, is 6 minus 3 times 3, right? Because you have 2 times 3 and then another 3. And then A5 is A4 minus 3. Of course, this is A4, so you put that in there. You're going to have, you're going to have 6 minus 3 times 3 minus 3, which is 6 minus 4 times 3. And if you write it all this way, then you can look at this, right? And if you compare this, right? So let me just write this. Let's write this. I'm just rewriting it, so I'm not doing a new term. I'm just rewriting. A5 equals 6 minus 4 times 3, right? I bet you could guess this. Guess at AN. So AN, if you look at the picture, probably is 6 minus, and compare this number here to this number here, right? This number keeps changing, the 4. Like, look at that number. You have a 2, a 3, a 4. So it's always one less than the number here. So what would it be if we had an n? It would be AN is 6 minus n minus 1 times 3. And this is your formula. Of course, you'd have to work it out. Simplify. If you simplify it, you would get 6 minus 3 times n is 3n. And then 3 times negative 1 is negative 3, but there's a minus out front, so it would be plus 3. And that would be 6. No, it wouldn't. That would be 6 plus 3, which is 9 minus 3n. Okay, so that's another way to get that formula, right? 9 minus 3n. But, you know, is that really a better way? I don't know. But that's the way the book, or the homework anyway, would advocate that you solved for that. Now, the only reason I'm showing you that is because there is kind of a trickier version of it, and you have to know a thing that we haven't seen yet. Okay, so one type of recursive formula will require you to know this weird fact. I'll say an interesting fact instead of a weird fact. Okay, so here's the thing. So let's say I take these numbers. Let's say I go 1. Actually, I don't like that color. What color is a good color? Blue. 1 plus x squared plus x cubed plus ... plus x to the m is equal to x m plus 1 power, it's an m plus 1 power minus 1 over x minus 1, and this is if x is not 1. Okay? Now, that's confusing, right? Like, why would you even care about that? But it's good because it lets you shorten a big long string of something into a short formula. So as an example, like, let's look at this example. 1 plus 3 plus 9 plus 27 plus 81, right? If you add that up, that's, I mean, I have to get a calculator, but 1 plus 3 plus 9 plus 27 plus 81 is 121, right? Just on a calculator. But if you write it in the form that I have up there, and 1 plus 3 plus 3 squared plus 3 to the 3 plus 3 to the 4, right? Then what you got is, well, I put a 5 there. Okay, sorry. Let me fix this. I have no idea why I put a 5 there. That's got to be an m. All right. If you compare these exponents here, right, whatever one you stop at is m, and then the one here is m plus 1. So if I stop at the 4, then when I write my formula, it would be the 3, that's the x, to the m plus 1, which is 5, right, 1 higher, minus 1 over 3 minus 1. And when you look at it this way, it's not so complicated of a formula, right? 3 to the 5th minus 1 over 3 minus 1. And if you write that out, hopefully we'll see that it's correct. So on the bottom we got 2, and then on the top, 3 to the 5 minus 1 is 242, which is in fact 121, right? So it's 121, and if you add it up, it's 121. Okay? Now the reason, well, not the reason, but you need this because I'm not sure if you're going to be able to guess the pattern for certain problems unless you have this. So that is why I wrote it, because I think you're going to need it. So let's look at an example and we'll see of where you'll need this. So A1 is 2. AN is AN minus 1 plus 3 to the n minus 2. Okay? So that's an interesting pattern, and this is for n greater than or equal to 2. So let's write out some terms. We know that that's how we have to get started anyway, right? We gotta see what's going on. So A1 is 2. Okay. A2 is going to be, well, according to the pattern here, the formula is the previous term plus 3 to the n minus 2. So n minus 2 is going to be 2 minus 2. Okay? So that is 2 plus 3 to the 0. All right? And I'm going to highlight this because I think this is how... no, that's fine. So that is actually 2 plus 1. Okay? Okay. You could write that as 3 if you want. But I think this is where we're going to have to pay attention to. So a 3 is a 2 plus 3 to the 3 minus 2. So it's you could write it as I'm gonna use this. Oops. I'm gonna use this form of it. So we're gonna have 2 plus 1 plus 3 to the 1, which is 2 plus 1 plus 3. And I'm going to leave it in this form. And then a4 is a 3 plus 3 to the 4 minus 2. So it's, what's a3? It's what I highlighted, 2 plus 1 plus 3 plus 3 to the 4 minus 2 is 2. So it's 2 plus 1 plus 3 plus 9. Like that. Okay. And at some point you have to start figuring out what the pattern is. So let's just try to guess A5. So just looking at the pattern here. So just look at the highlighted things. 2 plus 1, 2 plus 1 plus 3, and 2 plus 1 plus 3 plus 9. So what if I said that A5 was going to be probably 2 plus 1 plus 3 plus 9 plus 27? Would you guess that that's correct? I think you would, right? And so what would A6 be? 2 plus 1 plus 3 plus 9 plus 27 plus 81, right? I think so. I think that's right. So if I had to do this, I would say, can we guess AN? So AN would be 2 plus, and then this part right here, that's 1 plus 3 plus 9 plus 27 plus 81. Those are powers of 3, right? So they are 1 plus 3 to the 1 plus 3 to the 2 plus 3 to the 3 plus dot dot dot. Where do you stop? What power do you stop at? Right? And you have to compare it. So like on this term right here, the n was 6, right? And 81 is actually 3 to what power? That's actually 3 to the 4, right? And here, n was 5, and the 27 was 3 to the 3, right? So you always stop comparing this number to this number, this number to this number. The number on the right is always 2 less, right? 2 less. So if we're doing AN, then we would stop at 3 to the n minus 2, right? It's always 2 less. So that's my guess for the formula. Okay. That's my guess. But that's not what we can type in. We can't type it in this way. Okay, what you have to do is you have to simplify the part in the parentheses. I'm just recopying it so I can write next to it. So this must be simplified with the formula. What was the formula? The formula was 1 plus x squared plus dot 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 up to x to the m was x to the m plus 1, I think it was, we'll check it, x to the m plus 1 minus 1 over x minus 1. Is that right? Yeah, that's right. So that's the formula. So comparing it to what we have, we're doing an, it's 2 plus, and the pattern is it's going to be this fraction. What's the x? Right? Comparing what we have here to what we have here, the x is 3, right? The x is 3, and what's the m? The m is the last power here, right? So what's the last power we have? N minus 2. So the m is n minus 2. So if we copy this, we're going to have x, which is 3, to the m plus 1, which is n minus 2 plus 1, and then minus 1, over x, x is 3, minus 1. So we get an is 2 plus 3 to the n minus 2 plus 1 is 3 to the n minus 1 minus 1 over 2. And that's actually what they expect you to type in. Pretty complicated. But I think you only have 1 or 2 of those. Most of them are much easier than that. Actually, I think you only have 1. Of course, you have to get it right and before you can move on. That's tricky. Okay, that's tricky. So come to office hours if you get stuck on that. But that's that. All right. So we have one kind of topic left. And this is going to be in the next lecture too, so I'm not going to go over it in too much detail as of yet. But I'll give you the very basics. Okay. So limits of sequences. This is just going to be very basic. So limits of sequences. So limits of functions. Like, what kinds of limits of functions do you know? So you could do the limit as n goes to infinity. No, you wouldn't, because it's a limit of function. You could do like the limit as x goes to infinity of, if I said like 3x over 2x plus 5. Maybe you would know that one, right? Do you know the trick? If you have the same degree polynomial on top and on bottom, then the result is going to be just the ratio of the leading coefficients. So your leading coefficients are 3 and 2, then your answer here would just be 3 over 2. That would be your limit. Oops. Okay. So you can do limits like that. You could also do other kinds of limits. Let's see here. Let's fast forward a little bit in this homework assignment. You could try to do a limit like this. Limit as x goes to infinity of, what if I did 4 plus x squared? What would that limit be if x goes to infinity? Probably infinity, right? Yeah, probably, right? That's what it would be. Okay. So you can do limits like that. You could do a limit like this, like limit x to infinity 5 minus 1 over x squared. Now, if you had one like this, that looks really complicated, right? But it's not really complicated. All you would have to do is you would just say, well, you're putting in an infinity. Technically, you're not allowed to plug in infinity, but if you pretend that you can plug in an infinity down there, like that, you'd end up there. What is 1 over infinity? That's 0, right? So it's actually 5 minus 0 squared. And then what's 5 minus 0 squared? 5 squared is simply 25. So it's not that hard, right? Like you can just plug in, as long as you know that 1 divided by infinity is 0, then that's not too much work, right? So you can do limits like that, but those are limits of functions, not sequences. But guess what? Limits of sequences work exactly the same way. Okay, so it's easy just to do this. So if we say, you know, how do I want to do that? There's even a theorem that relates them. So I'm going to give you the theorem just to, hopefully make it a little simpler for you. The theorem itself will be confusing, but afterwards it should be easier. So suppose we have a sequence. So if AN is a sequence, and if f of x is a function, actually I'm going to say continuous function, with f of n equals an. Now I know that that's the part that's kind of confusing here. Then the limit as n goes to infinity of an is the same thing as the limit as x goes to infinity of f of x. Okay, and then this relates limits of functions to limits of sequences. All right. Now that's a complicated looking formula. Okay. I realize that somehow I managed to not actually give you the definition of convergence of a sequence, so I'm going to do that real quick. Actually, I better just move this down. Sorry. Move too far down. All right, let's go there. Let's actually give a definition of a sequence. So the definition of convergence of a sequence is this. So consider a sequence. Actually, I'm going to draw a picture of it. There we go. Right, so if you've got something like this, so if I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm done. I'm just going to put tick marks. All right, so a sequence is not like a curve, okay? A sequence is just a bunch of discrete points. So if I plot AN here and I plot N here, so not y and x, but n and an, then you might have a graph that looks like this. So like you might have a dot there, and then you might have a dot up here, and then you might have a dot down here, then you might have a dot here, and you might have a dot here, right? Then you might have a dot down here. And so you just have these dots and they're just wherever they are. Okay, so maybe this is a graph of my sequence. Okay, and what I was trying to draw there was, like, as we head out to the right, the ANs are getting closer and closer to some value L on the y-axis, right? And so if that happens, that's what we mean when we talk about the limit of a sequence. But there's a precise mathematical definition, which I will write. If I give myself more room yet again. And just scroll. Let me scroll. All right, so here's the definition. So we'll say this definition. For every epsilon greater than 0, that's just a small positive number. Sorry, I have to write if for every epsilon greater than 0, that's just a small positive number, there is an integer, positive integer, capital N, such that little n greater than n, or greater than or equal, it doesn't matter how you write it, I'll just say greater, n greater than capital N implies that an minus L absolute value is less than epsilon. So if that happens, then we say the limit as n goes to infinity of an equals L. Okay? That's the definition. Now, that's not something you're going to be using for calculations, but the idea is this. So if you pick an epsilon here, so like this is L plus epsilon and this is L minus epsilon. So epsilon is just this little distance. Okay? So you pick an epsilon, and then that epsilon, if you extend that out on like the y-axis here, like that, then what you'll see is that at a certain point, at some n value, if you go past that n value, so it's about here, it's probably this one, maybe n is 8, maybe n is 8. All of the n's past 8 have the blue, which is the what's it called? Which is the sequence. All of them past n equals 8 has the terms of the sequence in between L minus epsilon and L plus epsilon. Okay? So what that's saying is past n equals 8, the sequence is close to L, right? L is this value on the y-axis. And the definition says every epsilon greater than 0 that happens. So that means if you shrink it, if you shrink this interval to like here to here, you can still go out far enough and all of the blue dots will be in this little interval instead. You have to go out further than 8, but it'll happen. Even if you pick a little teeny tiny interval around L, you might have to go out 1,000 terms, but eventually all of your blue dots, which are will be in there, very, very, very close to L. And if that happens, that's what we mean. Oops, I need to just do that. That's what we mean when we say a sequence has a limit. Now, nobody uses that definition for calculations. The way you do calculations is with this theorem, which just says you can do limits of sequences the way that you do limits of functions, okay? Because that'll let you do this. Everything you know about limits of sequences, you can apply. Everything you know about limits of functions, you can apply to limits of sequences. So, like example, like, let's see. Find the limit if it exists. And then they say e to the parentheses 8 plus 8 over n squared, right? So the idea is this. Limit as n goes to infinity of e to the 8 plus 8 over n squared. And you can apply the theorem. You don't have to, but you could apply the theorem. And what the theorem lets you do is just say, well, you can just replace your n's with x's basically, and just say, well, anything you know about limits now you're allowed to do. That's what it comes down to. I don't know why I just did that. Okay. Now you don't have to do that, but if you want to look at x's instead of n's, you can. And then anything you know about limits, you can apply. Now this is actually a very easy limit, just like the previous one we did. If you think about just plugging in infinity, even though technically you don't plug in infinity, it's that, right? But then what is 8 over infinity? It's just 0. So what is the limit? It's just e to the 8th. And so that's the kind of, that's the type of limit that it looks like you're going to be doing here. Let's try another one. Evaluate limit as n goes to infinity of cosine 5 pi over 2 plus 4 over n to the 7. All right, I'm not going to use the theorem this time. What would I do? Just think about plugging in infinity. So just plug in infinity. 5 pi over 2 plus 4 over infinity, right? Infinity to the 7, but that's just infinity. What's 4 over infinity? 0. So this is just cosine 5 pi over 2. Now, use a unit circle or probably more likely a calculator. 5 times pi over 2, it is 0. So there you go. Simple. All right. And so that's the level of limit that you have. Now, one thing I'll tell you about Newton, so this is for Newton. So if the limit exists, well, this is not just for Newton. If the limit exists, why that didn't work? If the limit exists, we say it converges, just like we do for an integral. If the limit does not exist, we say it diverges, just like we did for the integrals. On Newton, if it diverges, you have to type this symbol in the box. This is not a 0. It's a symbol for the empty set. Why? It just stopped writing. Did my pen just die? Hold on a second. Apple Pencil. Yes. Does my Apple Pencil have no charge? Is that what you're telling me? I believe you are. Oh no. My Apple Pencil has no charge. Okay. Well, that's embarrassing. All right, so here's what's going to happen. I'm going to tell you what you're supposed to do. So if you have to type in that symbol, you're not going to see it on the keyboard at the beginning. What you're going to have to do is if you click in the box and it brings up the little on-screen keyboard for you, then it'll say algebra next to a keyboard symbol. And if you click on the algebra and scroll down, you'll find sets. And if you click on sets, then you'll find the symbol that you have to type in. Okay, so it's in the sets keyboard. Now what I'm going to do is I'm going to stop this video here because you know how to do everything. And then when my Apple Pencil charges and I can write on this again, I'm going to write that down, and so in the notes you'll see it. But right now you won't because all I can do is touch it with my finger. Anyway, so that's it. Good luck with the homework. I'll see you next time.